Hello students, in this video we will do the last few problems from chapter 1. And this first problem, number 17, has a block sliding down an inclined plane where the height here, the total height that it goes down is 20 meters and the length along the plane is 40 meters, and you are told the plane has no friction and you are asked how long it takes the block to slide down. Now, it will not matter how massive the block is. We're assuming no friction and also nothing like wind resistance or anything. And you remember in the last video I told you that these inclined plane problems are always, so let me write number 17. So the last video I told you these inclined plane problems are always determined by two forces going in opposite directions. One is mg sine theta, and this is the component of the gravitational force going down the plane, versus friction. Well, here there's no friction. So the net force on the mass is just mg sine theta. Now, what's sine theta here? Well, remember sine theta is always the theta, by the way, is the one over here. That's the angle of the plane. It's always the opposite over the hypotenuse. So what this comes out to be is the mass, whatever that is, and it will turn out it doesn't matter. The g is, I could write 10 or minus 10 depending on what I want to say is the positive direction. I'm going to just write 10, and I'll put in the units later. So this is 10, and then sine theta, that's 20 over 40. So this is 20 over 40. So that force is equal to just, well, that 20 over 40 is 1/2 times 10, so this is just 5m. Now, Newton's second law says that that force is equal to the mass times the acceleration. So I have two equations here for the same thing, force here, so I can set those equal to each other. And so what I get is 5m equals ma. Now the m's cancel on both sides, and I get just acceleration a equals 5. Okay, so now I know the total distance, I know the acceleration, and I can solve for time. Now the equation I'm going to use is the equation from way back, x minus x0 equals v0t plus 1/2 a t squared. Now I'm going to assume the initial velocity is 0. The problem doesn't really say so, but it kind of implies that. So this part would go away. I'm going to say that the starting point up here where it starts is 0, so that would be the x0. The final x is 40 because it goes a distance of 40 here. So that will say that this here is 40 equals, now the a, I just found the a is 5. So this is 1/2 times 5 times t squared. And so then I could multiply both sides by 2 and divide both sides by 5. So I would get 2 divided by 5 times 40 equals So this will be 1/2 5, and then, well, I guess I multiplied it by 2/5, right? So the 2/5, the 1/2, and the 5 t squared. And the reason I did this is to make the 2's and 5's cancel. So this says t squared equals, this is 40 times 2 is 80 divided by 5, which is 16. And so t, well, you can't have, you could say plus or minus 4, but you're not going to have a negative time here, so t equals 4. And that's your answer. And that comes out to be answer choice C on the problem. Okay. So number 18 is a conceptual problem, which means that you're not putting in specific numbers, you're just answering a qualitative question about what's happening. And so what it says is you have a mass on an incline here, and the incline is tipping further over. And it asks you, how do the components of the gravitational force, the one parallel to the plane and the one perpendicular to the plane, how do these components change? So we could redraw this. You know, you could have this, imagine that this is a like a seesaw sort of mechanism, and this part's going up and this part's going down. It's tilting more, and you have this mass here. And so you've got the component going this way, the component of the gravitational force going this way, and you've got the component going down. How do those change? Well, you remember what this one is. This is mg sine theta. This is mg cosine theta. If you know how sine and cosine work, then you could answer it mathematically without thinking of what's happening physically. This one gets bigger and this one gets smaller. Of course, that's what you expect to happen physically too, because the more you tip it, the more inclination it's going to have to slide down the plane, and that's the same thing as saying that the component of force along the plane, parallel to the plane, increases. So what the answer is that mg sine theta, this part that's parallel to the plane, that force increases, and mg cosine theta decreases. And that's answer choice A. Okay, now and I forgot to write number 18. I still had 17 up there, but of course it was 18. Now for number 19, so what it says is you have this boat. So here's your boat, and it's on the water. And there's a dock here. And it says that there's a bunch of used tires attached to the dock in order to cushion the boat. See, the boat's coming in this way, and it's going to hit the edge here, and so it doesn't damage it. You have these tires there to cushion it. So what I'll do is I'll just draw, like I'll erase part of this, and I'll just draw like one tire sticking out here. So this is one tire. And so when this hits, what's going to happen is the tire is going to deform a little bit, and it'll slow down the boat. So you can have a bunch of, other tires on here. The boat's going to hit that. I guess maybe this could be a sailboat. That's a rather pathetic looking sailboat, and then here's a little person in there. So what the question asks is, how does the force exerted by the tire change after? So the boat hits the tire. So what's happening in slow motion looks like this. The boat has just barely gotten. It's just now barely hitting the tire, and then so this is like this, and so this is well, I don't want to use A because then it looks like that A. So this is A, B, this is what happens next. It just hits the tire. And then next it hits the tire and it deforms it a little bit. So here it's just now hitting. So here it just hits. So now here it's actually pushed up against the tire. There, I dropped my little eraser here. It's pushed up against the tire, and so maybe this is part C. And then when it finally comes to a stop, it's going to be, and so the tire is going to be compressed even more. And this isn't a very good picture, but you get the idea. So the boat is really pressed up against the tire now. It's going to stop, and then of course it's going to rebound off. So this is D, and then what's going to happen? So here it's really here, so it's in the process of hitting it. So it's pushed up against it, and then what's going to happen afterwards is it's going to, so this whole time it still is heading in this direction, and then it's going to rebound off. So the tire's going to push back out, and it's going to rebound off. It's going to come this way. And so, but this is the point at which we're interested. This is the point at which it has stopped, and the question asks, well, the force that's being exerted by the tire on the boat, does that force increase or decrease until the boat stops? And so this is a Hooke's law question, and this shows you how something other than a spring can exhibit this same behavior, this deformation, resistance, restoring force, like what a spring does. The answer is that the force increases. So the force exerted by the tire increases up until this point where the force is finally enough to stop the boat and start pushing it back the other way. The reason why is because it takes more, the more you press on the tire, the more it will deform, and the other way of saying that is the more it's deformed, the more force it takes to deform it that much. So the point of maximum deformation is exactly when the boat stops, and then it starts going back the other direction, and the tire starts expanding out again. So the answer here would be that the force increases until stopping, and that's answer choice C. All right, and then we have number 20, and here this is another Hooke's law question. It has two masses, and I will redraw this a little bit bigger. It said you have two copies of the same type of spring, and one has a mass of 1 kilogram hanging from it, and the other has a mass of 1.5 kilograms hanging from it. And it said, what the problem says is that this one is extended 6, I think it said 6 centimeters, I think it was centimeters, not meters, I don't remember. And this one is extended 7 centimeters. And so in particular, the distance between these, so if I measure the distance between how much these are extended, that's 1 centimeter. And so the question was, what's the spring constant? And so you remember that the idea, so the spring constant, and the spring constant is going to be the same in both cases. That's what it tells you that it's the same, it's copies of the same spring. So you're assuming it's the same spring constant. And so the difference is that this one has more force applied to it because it's 1.5 kilograms, whereas this one just has 1 kilogram. And so this one, the force that's being applied here is going to be 15 newtons, because what is that? Well, that's this is mg, So the m is 1.5 kilograms, the g is 10 meters per second squared. I could put a negative in there because it's going downward, but I'm saying 15 newtons in the downward direction, so we won't worry about that, whereas this one is 10 newtons in the downward direction. So what this says is 5 more newtons gives you 1 more centimeter of stretching. And so this is sort of a informal way of saying that the spring constant K is 5 newtons per centimeter, because it takes 5 newtons to deform it another centimeter. And that is answer choice B. It was answer choice B on this one. And I forgot to label that one as 20. So I've done 17, 18, 19, and 20, but it said 17 for part of the time I was doing 18, and it said 19 for part of the time I was doing 20. I think it was pretty clear which ones we were doing. So here is 21. And what this one says is that you have a mass sitting on the surface of the Earth. So this is Earth. And it says, okay, well, the Earth exerts a force, a downward force of mg on the mass. And it says, you know, so Newton's third law says that there should be a reaction force. For every action, there's an equal and opposite reaction. There's this force exerted by the Earth on the mass. So there should be a reaction force. What is the reaction force? And for it to be an equal and opposite reaction, it has to be, well, to be opposite, it has to be exerted on the Earth by the mass. And for it to be equal, it has to be the same size as mg. And so what the answer is that it's the gravitational force of the mass on the Earth. Now you might think this seems ridiculous because you don't think of a little mass as exerting a gravitational force on the Earth, and certainly not the equal force that Earth exerts, because the Earth doesn't move at all as far as you can see, whereas the mass moves very noticeably. If it's, you know, if you drop it, it will fall. But it's actually true that the force that the mass exerts on the Earth is the same as the force that the Earth exerts on the mass. It's just in the opposite direction. And this comes from Newton's universal law of gravitation. You could, I don't think you'll have to remember this. It wouldn't hurt. But it says that the force of gravitation between two masses, in this case it's the mass of the Earth and this mass, is some constant called g, which is, it's just a number. You don't have to remember it. It's like 6.67 times 10 to the negative 11th or something. And then you have big M, so this is the mass of the Earth. And then you have little m, and so that's this mass here, divided by r squared, where r is the distance from this, well, in this case it's the distance from the surface of the Earth to the center of the Earth. You think about, here's the Earth, so you're zooming way out into space, and here's your little mass. And so this is the distance, this radial distance to the center of the Earth. That's r, that distance there. And so you see, this is the same force. There's the mass of the Earth and there's the mass of the object in here. This says that the size of the force exerted by the Earth on the object is the same as the size of the force exerted on the Earth by the object. Same thing. So that's a little counterintuitive maybe, but that's how it works. See, the thing is the Earth is so large it would take, you know, Newton's second law, this F equals ma, for you to notice the Earth moving as a result of the gravitational force of this little mass. This change in motion would be the acceleration. This would be acceleration of the Earth. But the mass of the Earth is so great that it makes the acceleration very small. See, the mass here is so great. In this case, this would be mass of the Earth times whatever the acceleration is, and the force is not very big. I mean, that force is just little m times g. Well, the mass of the Earth is huge, and so the acceleration will be very small, and you won't notice it. Too small to notice. That was answer choice B, by the way. Now for 22, this is something where, just based on physics itself, the question doesn't give you enough information to answer the problem. You have to know something about this size exclusion chromatography thing. So it says, all right, well, there's this, you're doing this size exclusion chromatography. Now, the way this works is like you have some kind of a cylinder or something, and you have, this goes down to the bottom, and then it has like a funnel or something, and it comes out. And then, so inside the cylinder are these kind of porous beads. So these are like plastic beads that have holes in them. And then you put some molecules into here. And some of them are big and some of them are small. And these are typically, in this context, they're large organic molecules like proteins. And so you have some really little ones, you know, proteins are often like folded chains, and then you might have some bigger ones. And these will diffuse down through this cylinder, and they'll run out at the bottom. And so you keep on running this solution through here. You know, maybe you put these molecules in here. Maybe you're running these in from like a hose or nozzle or something. So, you know, these are running in here. And they keep on running through, and then they run out at the bottom. And the whole point of this is to separate the big ones from the little ones. And so what the question asks is, do the big ones come out first or do the little ones come out first? And this word elute means come through, essentially. It says, do the big ones elute first or do the little ones elute first? And the mechanism that's going on here is that the little ones get stuck in these holes. And, you know, maybe then they can come out. But the big ones have an easier time going through. You know, so the big ones come through, they have an easier time going through, whereas the little ones tend to get stuck. It's actually a pretty crude process in some ways, in the sense that it's not going to necessarily separate everything out neatly, because some of the little ones will miss it and they'll come through with the big ones. But the big ones will come out first, by and large, because they avoid getting stuck in the holes in the beads. And so the answer they want you to give is answer choice A, which says that the big ones come through first because they experience less frictional force as they're going through, whereas the little ones get caught. And so that's one of those contact forces. That's one of those types of friction where it's two objects coming into close contact with each other. But this is really not a physics question. Unless you knew about size exclusion chromatography, there's no way you could answer the question. So that's kind of it's more exclusively I don't know, I mean, this isn't used exclusively in medical settings. It's used a lot in industrial settings as well. But in any case, that's supposed to be the answer, and that's answer choice A. Okay, and then we have number 23. Now this is similar to a problem that we looked at before. And this says that, you remember we had a problem where we had a mass that was in free fall? 10 kilograms, and so it was going down at minus 10 meters per second squared. And the answer was, how much force would you need to apply to make it go back up at, so this is to make it go back up at 10 meters per second squared, and the answer was 200 newtons in that case. This is almost the same problem. In this one, though, you have a mass that starts out just sitting here, and it's 10 kilograms. And the answer is, well, how much force do you need to make it accelerate upward at 5 meters per second squared? And it's the same strategy, so this is the same idea as before. And that is that you need to overcome the gravitational force which of course is mg, and provide 5 meters per second squared of additional acceleration. Because if you just cancel out, if you just apply enough force to cancel out the mg, that would just make it sit there. It would be like just enough, like you're just about to lift it up, but it isn't quite lifting up yet off the plane. Whereas if you apply some additional force, then it will start to accelerate upward, and how much force do you have to apply? Well, to overcome the gravitational force of mg, that's mg, the m is 10, so that's 10, and what's g? That's a minus 10 meters per second squared. So to overcome this, you need to have a plus this same amount, so this is plus 100 newtons you need, plus you need an additional acceleration of 5 upwards, so this is a force equals mass times acceleration thing. Mass times acceleration is 5 meters per second. Its additional amount is plus 50 newtons, and so there's added together to 150 newtons. And that's answer choice A. And then finally, number 24, and I don't know if it's a coincidence that this is the last problem, but this turns out to be one where they actually don't get it right, or they don't give you enough information, or their answer is not convincing, or whatever. And so what the problem is it says, okay, you have a tennis ball. Here's a tennis ball, and you drop the tennis ball, and it falls at a certain rate, and then you also have this feather. And you drop the feather and it falls at a much slower rate. And the question is, why does the tennis ball fall faster? And so what the book wants you to say is it's because the tennis ball has less surface area. Now this is a bad answer. For one thing, it's not obvious the tennis ball would have less surface area. I mean, that's got to be a pretty big feather. If it's one of those big, like peacock feathers or something, then yeah, I'll admit that the tennis ball has less surface area. But you could take a tiny, tiny little feather that has way less surface area than the tennis ball, and it will still fall much slower than what the tennis ball will. And so this would be a terrible explanation in that case. Furthermore, to make it even worse, if I take a little bullet, say I take a little bullet, well, that obviously has much less surface area than what the tennis ball does, yet it will accelerate downward faster. So this is just a bad answer choice. The point is that so what's better is to say that so it's the ratio. So the ratio of mass to surface area is what matters. Why? Because the force downward is coming entirely from the mass. It's mg, that's the gravitational force. Whereas the force upward, that's from drag, friction, wind resistance. And that's coming entirely from the surface area. So it's not that a large surface area always implies a small downward acceleration. I mean, you could drop a barbell down and it would accelerate down quickly. It has a big surface area. It's the comparison, it's the ratio between the mass and the surface area that matters. For the tennis ball, it's a large ratio of mass to surface area, meaning the mass is relatively large and the surface area is relatively small, comparatively speaking. Large, so you get large acceleration. And then for the feather, no matter how big the feather is, if it's a tiny little feather, if it's a big peacock feather, the ratio is small. So you get small acceleration. So they goofed on the last one, but we fixed it. So anyway, that finishes our videos for the first chapter.